Ever looked at a really complex 3D design and just wondered how? What's actually holding it all together?
Yeah, it seems like magic sometimes, doesn't it?
Totally. But it's not, right?
Yeah.
There's a real structure underneath. And if you're anything like me, you want to understand that structure, like quickly and properly, get those aha moments without wading through jargon.
Exactly. And that's what we're doing today. Welcome to the deep dive.
Today we are jumping into the fundamental data, the stuff that defines digital surfaces.
And not just surfaces, but how they link up, how they build into the complex 3D objects we see everywhere. We're drawing on a pretty detailed lecture and some briefing docs for this.
Think of this as your maybe cheat sheet for understanding the DNA of 3D geometry.
It's a good way to put it.
Our mission, really, is to unpack these building blocks. We start with a simple curve, give it another dimension,
That was a surface.
and then see how those surfaces combine into, complex things. Gadgets, buildings, you name it.
And the payoff is understanding this base level really gives you a shortcut to grasping much more advanced design concepts later on. It's foundational.
So the sources, you mentioned a lecture.
Yeah, a video lecture. It actually used some Python code examples to show how surfaces and Brep work.
Brep, boundary representation.
It's the one. And we also have briefing documents that summarize these ideas pretty clearly. So we've got the practical code angle and the core concepts.
Okay, let's dive in then. Surfaces. Sounds basic, but I get the feeling there's more to it. Where do we start? What's the absolute core idea?
Well, at its simplest, a surface is really just a curve that's been extended, give it another dimension.
Right.
The lecture put it nicely. Basically, once you understand the curve, we can add another dimension, then it's in text in the surface. It's a natural progression, 1D to 2D.
Okay, makes sense. So if we're talking data, the actual nuts and bolts inside the computer, what defines a surface?
There are a few key pieces of data. First, you've got the point grid. Think of it like an array, a structured set of points in 3D space. That gives the surface its shape and location.
A grid of points, got it. What else?
Then you have iso curves. You might hear them called U and V curves. They run along the surface, like latitude and longitude lines on a globe.
Ah, okay. The lecture mentioned those. U and V curve, the iso curve.
Yep, that's them. They define the sort of internal coordinate system of the surface.
So points for shape, iso curves for direction. What else is critical?
The normal vector, hugely important. It's the direction pointing straight out from the surface at any given point. Perpendicular.
Like an arrow sticking straight up.
Exactly. It tells you the surface's orientation, and it's calculated from the tangent vectors along those U and V curves.
Okay. And you also mentioned curvature.
Right, curvature. That describes how much the surface is bending or curving.
Bending, okay.
Yeah, concepts like slope, and then more specific measures like principal curvature. That's the min and max bending.
Min and max.
Gaussian curvature and mean curvature. These all help quantify the shape, the coverage, as we called it, how it curves in space.
Coverage, right. Gives you the overall form. Now, how do we actually, tell a computer about these surfaces? Are there different methods?
There are mainly two ways. Implicit and parametric.
Implicit.
That's where you define it with an equation. Like the equation for a sphere, x squared plus y squared plus z squared equals radius squared. The relationship between coordinates defines the shape. The lecture mentioned planes and spheres here.
Okay, equation-based.
Yeah.
But you said parametric is more common in design software.
Yeah, especially in tools like Rhino, that's parametric representation.
Parametric. We talked about that for curves. How does it work for surfaces?
Well, it's very similar, but like the lecture said, again, we have another dimension. So instead of one parameter, t, for a curve.
You have two.
Exactly. U and V. In this case, we have two parameters like U and V, right?
No.
These U and V coordinates define a point on a 2D plane, the UV space.
UV space, like a flat map.
Kind of, yeah. And this flat UV map is then mathematically stretched or mapped onto the 3D surface. Think of drawing a grid on a rubber sheet, then stretching that sheet into a 3D shape. The UV grid follows along.
Is this UV space always like a simple 0 to 1 square?
It can be normalized to 0 to 1, often is for convenience. But the crucial thing is the underlying domain, the original range of U and V values before normalization.
Why does that matter so much?
Because, as the lecture pointed out, that simple UV rectangle can get really distorted in 3D space. The plane is actually have no idea how they distort in the space. The software needs to know that original undistorted domain to correctly measure things like distance or area on the final 3D shape. It needs that reference.
Ah, I see. So the history of the stretching matters.
Precisely. So, okay, we have all this data. How do we use it?
Yeah, give me an example. Calculating area.
Area calculation is a great example. You can't usually calculate the area of a complex curved surface directly. So what the computer does is approximate it. It breaks the surface down into tons of tiny flat triangles. A mesh, essentially.
Triangulation.
Exactly. Calculate the area of each tiny triangle, add them all up. The lecture showed a sort of pseudocode snippet for this.
Like Python code.
Yeah, Python-like. It had a placeholder variable and a double loop using do and dv.
Do and dv, small steps in UMV.
Right, representing how finely you divide the surface. It just shows the logic, the behind-the-scene calculation.
So lots of tiny additions. Makes sense.
And besides area, this data is used for other things too, like point projection.
Snapping a point onto the surface.
Yeah, finding the closest point on the surface and getting its u, v coordinates. And surface evaluation.
Which is?
Giving a u, v coordinate pair and finding out everything about that point on the surface. Its 3D position, the tangent vectors, the normal vector, the curvature.
All from the UNV?
All from the UNV. Oh, and a quick note. To get an accurate normal vector, you first need to normalize those tangent vectors, make them length 1.
Got it. Normalize the tangents first. Okay, let's dig deeper into that bending. Curvature. What does it really tell us?
It's about quantifying the bend. So think of a sphere, perfect sphere. It bends the same amount in all directions at any point, right? Uniform curvature.
Makes sense.
Now, a cylinder, it curves around, right, but along its length.
It's straight.
Exactly. So it has curvature in one principal direction, but zero curvature in the other. That makes it what's called a developable surface.
Developable? Because you can develop it, flatten it out.
Precisely. We'll come back to that. It's important. So different shapes have different curvature signatures.
How do we measure these differences? You mentioned Gaussian mean curvature.
Right. Gaussian curvature, often written as K, is found by multiplying the two principal curvatures, the min and max bending.
Multiplying them.
Okay. If K is positive, the surface is locally like a sphere or an eggshell bending the same way.
Like a dome.
Yep. If K is negative, it's saddle-shaped, bending opposite ways, like a Pringles chip or, well, a saddle.
All right, got it. And if K is 0?
That means it's flat in at least one direction. So it could be planar or, like our cylinder, developable. The lecture mentioned that in visualizations, K0 often shows up as black.
Black means 0 Gaussian. Useful tip. And mean curvature, H.
Mean curvature H is simpler. It's just the average of the two principal curvatures. Gives you a general sense of the overall bending at that point.
Average bend. Okay. Now back to that developable idea and flattening things out. Surface mapping.
Yes, surface mapping. The core idea is that any surface, however wrinkly in 3D, can theoretically be unfolded or mapped onto a flat 2D rectangle in that UV space we discussed.
Like peeling an orange and trying to lay the peel flat.
Exactly like that. It creates a direct link, a mapping between every 3D point and a unique 2D point on the UV rectangle.
But you can't peel an orange perfectly flat without tearing or stretching it, right? So there must be trade-offs in this mapping.
Absolutely. You generally can't preserve everything, angles, areas, and lengths all at once when you flatten a curved surface. You have to choose what's important.
So different types of maps prioritize different things.
Correct. There are 3 main types based on what they preserve. First is angle preservation.
Like the Mercator map projection.
Perfect example. The lecture said, in this map, we preserve the angle, the direction of the map here. Crucial for navigation because compass bearings stay true, but...
areas get massively distorted near the poles. Greenland looks huge.
Right. This conformal mapping, preserving angles, is also vital if you're applying textures to 3D models. You don't want the pattern to get sheared or distorted.
Makes sense. What are the other types?
Second is area preservation. These maps maintain the correct relative sizes of regions. Shapes might get warped, but a square mile on the map represents a consistent actual area, important for statistical maps, land use, that kind of thing.
Okay, preserving area size. And the third?
Length preservation, also called equidistant mapping. Here, distances are accurate along certain lines, often radiating from a central point or along lines of longitude.
Like measuring flight paths.
Exactly. A flight path might look curved on one map, but be the shortest distance, a great circle route, which can be shown as straight on a specific length-preserving projection.
Fascinating. So you pick the map type based on what you need to measure accurately.
You got it. It's all about the trade-offs.
Now let's loop back properly to developable surfaces. You said they have 0 Gaussian curvature.
Correct. KO0 everywhere. And the magic property is they can be flattened perfectly into a 2D plane without any stretching, tearing, or squashing.
Like cones and cylinders.
Those are the classic examples. You can literally cut open a paper cone or cylinder and lay it perfectly flat.
Why is that useful?
Think manufacturing. Sheet metal, fabric patterns. If you can design a shape using developable surfaces, you know you can make it by simply bending a flat sheet of material. No complex stretching or forming needed. Saves cost, simplifies things.
Ah, practical application. Okay, now, slightly different track.
Yeah.
Finding the shortest path on a surface. Not through space, but sticking to the surface.
That's where geodesic curves come in. A geodesic is the shortest possible line between 2 points that stays entirely on the surface.
Okay, how do you find that?
The lecture's analogy was great. Think about it like there's a 2-point, what is the shortest line to connect 2 red dots on the surface itself?
Right.
The conceptual trick is, imagine you could unfold that developable surface, or even a non-developable one conceptually, into a flat plane.
Okay, flatten it out.
Draw a dead straight line between your 2 points on the flat version.
Simple enough.
Now, fold the surface back up into its 3D shape. That straight line you drew on the flat pattern becomes the geodesic curve on the 3D surface. It's the shortest route following the contours.
That's a really clear way to visualize it. Unfold, draw straight, refold. Love it.
It works conceptually even for surfaces you can't physically unfold perfectly.
Right. Now we've got the surfaces we understand, bending, mapping, shortest paths. How do we actually build complex stuff? The lecture mentioned NURBS and Brep.
Okay, so NURBS surfaces. NURBS stands for non-uniform rational B-splines. Big mouthful.
Ah, yeah.
But they're basically a super flexible mathematical way to define smooth curves and surfaces. Very common in CAD, like Rhino. You control them with control points.
Like pulling handles to shape the surface.
Kind of, yeah. They give great local control. But mathematically, a single NURBS surface patch is often based on a four-sided structure, topologically speaking.
Four-sided. So what if your shape isn't four-sided? Or has holes?
That's the limitation.
What?
It can be tricky to represent complex topologies things with branches, holes, more or fewer than 4 sides with just one single NURBS patch.
So how do we deal with that?
One way is using trimmed surfaces. You start with a larger, often simpler NURBS surface, maybe rectangular, and then you define boundary curves on that surface to cut parts away, like using a cookie cutter. You can trim a hole out or trim it to a non-rectangular shape.
Ah, so you modify the basic patch. That gives more freedom.
It does, but what if you need to join multiple distinct surface pieces together, maybe some trimmed, some not, to make a really complex object?
Yeah, like assembling parts.
That's where Brep comes in. Boundary representation. It's a method for describing complex, solid shapes by explicitly defining their boundaries, the surfaces that enclose them.
So it's about the skin of the object.
Exactly. Brep lets you combine multiple surface patches, including trimmed ones, into a single, coherent model. The lecturer used a hammer as an example.
A hammer. Okay, I can see that. Handle, head, different parts.
Right. Because of the limitation of the set piece here, sometimes we need to assemble or disassemble more than one side pieces in order to, resolve the drawback. We should understand the poly service, which is nothing special, just like a tacky multiple patchworks, like trimmed the side piece to describe this hammer.
Polysurface. Is that Rhino terminology for a Brep object?
Often, yes. It represents a collection of joined faces or surfaces. Understanding Brep is key for operations like Booleans cutting one shape from another, because the software needs to know how all these boundary surfaces connect and interact.
So Brep is the framework for complex assemblies. How is the data structured? Sounds like it could get messy.
It needs to be organized, for sure. Brep uses a hierarchy.
A hierarchy, like levels.
Yeah. At the top, you might have a compound object that contains shells. A shell is a set of connected faces enclosing a region.
Okay, shell.
Each shell is made of faces, which are the individual surfaces, possibly trimmed.
Faces.
Each face is bounded by one or more closed loops.
Those loops, the edges.
Loops are made of edges, which correspond to the underlying curves defining the boundaries.
Right.
And finally, edges connect at vertices, the points.
Wow. So object shell, face loop, edge vertex, down to the points.
Pretty much. And if a Brep object fully encloses a volume with no gaps, it's typically called a solid.
It's quite a detailed breakdown, very structured.
It has to be, for the computer to make sense of it all.
Now, you also mentioned mesh data earlier. How's that different from Brep?
Mesh is another super common way to represent 3D forms. It can have a hierarchy too, but its fundamental definition is different.
How so?
The absolute core of a mesh is its vertices, just a list of points in 3D space, XYZ coordinates.
Okay, a cloud of points.
Well, a list of points. Then the critical part is the faces. Mesh faces are usually triangles or quads, four-sided polygons.
Right.
And these faces are defined simply by listing the indices, their position number in the vertex list, of the vertices they connect. So a triangle might be defined as connecting vertex 0, vertex 1, and vertex 2 from the list.
Ah, so it's point coordinates and then connection information, like
Yep.
connect the dots.
Exactly. The lecture gave an example, like face 0, 1, 5, 4 foot, meaning connect vertex 0 to 1, 1 to 5, 5 to 4, and 4 back to 0. That's the connectivity.
Okay, and meshes are used a lot for.
Huge for things like 3D printing, animation, game engines, simulation. They provide this discrete, faceted representation that's easy for graphics cards and printers to process.
So Brep is mathematically precise surfaces, mesh is points in connection.
That's a good simplification, yes. Brep knows about the smooth, continuous surface definitions. Mesh primarily knows about vertex locations and which vertices form each polygon face.
This is really clarifying. But stepping back,
Mhm.
why does knowing all this matter so much for someone actually doing design work?
Oh, it's crucial. If you want to go beyond just using the standard tools in your software,
Like scripting or automation?
exactly. If you want to use the software's API, its application programming interface, to write your own tools or custom workflows, you have to understand how it represents geometry internally. Is it using Brep, Mesh? How are faces and edges stored? You need to speak its language.
Right, to interact with the data directly.
And beyond APIs, it helps you develop smarter design strategies. Knowing the difference between a NURBS surface and a mesh helps you choose the right tool for the job, anticipate potential problems, and think computationally. The lecture actually mentioned that understanding object-oriented programming.
Which is coming up next for us.
Right. Understanding OOP alongside these data structures gives you a completely new perspective on the design world, a more powerful way to engage with it.
Unlocks new possibilities.
Okay.
And you mentioned this is part of a larger course structure. How does this fit in?
Yeah, so we started with vector graphics basics. Now we've done this deep dive into surfaces and Brep Mesh. This sets the stage perfectly for our next session on object-oriented programming.
Seeing how to structure code around these geometric objects?
Precisely. And after OOP, the plan is to explore discretization, how we turn continuous things into manageable chunks.
Like meshing.
Related, yeah. Then graph data structures, which are relevant for connectivity, machine learning and design, and finally visualization. It all builds on these fundamentals.
Sounds like a solid progression. And all these deep dives, plus our own research and diagrams, that feeds into a final project.
That's the idea, your own explorations, maybe diagrams you make in Lucidchart or whatever, the homeworks. It all comes together. The lecture suggested a research paper structure, abstract, intro, etc., as a possible model.
But not strictly required.
Not required like a formal paper, no. I'm not expecting like reading paper at the end of a class, but it's good to have that structure make sense. Okay, so I'm not asking you a homework for homework. This is individual material, like let's say this Lucid chart and individual research, and all homeworks will assemble into one piece for the final project. The main thing is pulling your learning together coherently.
Got it. Makes sense. Phew. Okay, well, that was quite the journey. From curves to surfaces to complex breps and meshes.
We covered a lot of ground, but hopefully the key takeaway for you listening is clear. Getting a handle on these underlying data structures, how surfaces are defined, how they're combined in Brep, really unlocks a deeper understanding.
Yeah, it's like seeing the code behind the matrix, almost.
It empowers you to think beyond the surface level, literally, and grasp the potential of digital design tools much more fully.
So here's something to maybe mull over. Now that you have this insight, this glimpse into the building blocks, how might you think differently about creating 3D forms? What new ways of manipulating or combining these structures pop into your head?
What possibilities does knowing about UV space or developable surfaces or the Brep hierarchy spark for your own creative ideas?
Definitely something to think about.
And we really encourage you to keep exploring these ideas. Maybe even peek ahead at object-oriented programming and consider how it connects back to managing all this geometric data we've talked about.
It definitely feels like a solid foundation for digging deeper into computational design.
Absolutely. It's an exciting space, and understanding the fundamentals is the key to unlocking its potential.